Greetings, I'm Aman and I'm excited to talk to you about our new work that deals with calibrating deterministic errors of an accelerometer. But before we begin, it's important to first understand what an accelerometer is and what does it measure. An accelerometer measures specific forces or the acceleration with respect to gravity. Alongside gyros, they constitute an inertial measurement unit or an IMU that you can see on this board. These IMUs are used in various products such as cell phones, smartwatches, rehabilitation devices, drones, and autonomous vehicles. Having said that, the accelerometers are not perfect. Their measurements are subjected to errors, and these errors can be categorized broadly into two: deterministic and stochastic. In this work, we are going to focus on identifying the deterministic errors, which include the bias, scale factor, and the non-orthogonality. The observation model of an accelerometer is given by the following equation. Here, Z represents the measurement, X is the ground truth, which is typically unknown, B represents the bias, and M is a lower triangular matrix having the terms associated with the scale factors and the non-orthogonality. To solve this system for deterministic errors, a static constraint is used. This results in a nonlinear model which involves 9 unknowns, and we use a multi-pose methodology wherein multiple observations of the IMU in different poses, as I'm showing here on the video, are used by using recursive least squares or iterative least squares. But this approach has two major drawbacks. First, it requires an initial guess, and the second, there is a need of multiple iterations. So, how do we solve it? We take the nonlinear model as it is, and then we combine it with our method to convert the nonlinear model into a system of linear equations. And then, as said earlier, we take multiple observations of the IMU in different poses to obtain a closed form solution of the deterministic errors that are the bias, scale factor, and non-orthogonality. Putting things in perspective, we test our method both in simulation and on the field. As you can see on the photos on the slide, our method is practical to obtain the switch-on bias of the accelerometer in 6 to 8 poses. Of course, this comes with an assumption that the scale factor and the non-orthogonality do not change much. For more details about the experiments, I invite you to read the paper. In conclusion, I want to talk to you about the primary advantages of our work. Our method is linear and therefore does not require any initial guess, nor does it have any requirements for multiple iterations. Therefore, our method to identify the deterministic errors of an accelerometer is around an order of magnitude faster than the existing ones. For more details, I invite you to read the paper and contact me.